Today's discussion is about extrusion versus film cast. Um, there are two ways of making tubes for catheter applications. One is extrusion, basically melting the pellets, polymer plates, and forming it into a tube. And the second is that to form it into a tube, you can dissolve your pellets or polymers in a solvent and then cast it on a mandrel or metal and then evaporate the solvents to make it solid and in a tube form. Basically, it's a deep molding or deep casting method. I have added one other topic for discussion here is injection molding because there are some parts in catheters or other biomedical parts that are injected molded parts, and therefore it is important to know what are the potential um, issues are with these injection molding part, how we can troubleshoot those, and how we can check the parts before use it in a product. So to review injection molding process, I have selected this video from YouTube. That is, I think, is a very good video that shows how the process is performed. So the pellets, I mean, is the same basically uh, principle of melting the pellets and use a screw and a barrel to push the material out. But the difference here between injection molding and extrusion is that the screw move um, moves axially, so it would act like a plunger. So when the material melts and fill the barrel, the screw will shoot the material into the mold. So it moves from right to left to push the material into the mold. And the mold has cavity in it based on what shape we want to basically forms. And when once the polymer is injected inside the mold and is filling the mold, then the cooling will be performed to cool the parts, and now the screw would go back to its initial position and the mold would be open and the part would drop off from the machine and the new cycle would begin. So that's basically the principle of injection molding process. Um, so for injection molding, the potential issues are warping, that is uneven shrinkage inside a part. Sink mark is that when you have like the inner side is cooling with a different rate than the outer layer. And weld line is that when the two piece, like when the mold is closing and the two cavities are merged, there is like a line that is very pronounced and is considered a defect. Flashing is when you have excessive plastic seeping out. And a very important thing that has been shown in this picture is anisotropy. And it means that there is residual stress left in the part that is pretty common with nylon material or polycarbonate material. These residual stress left in material can be detected through different methods like DSC or as it's shown here is with the polariscope. It would show that when the color turns blue is that the location that you have the highest residual stress trapped. And if it goes under stress or when you have like a glue or something, it could increase the chance of crack propagation in that regions. So that's something that you have to keep in mind with you are working with the injection molded parts. For film casting, I'm using the pictures from this website that is an article that has very good pictures that shows how film casting is performed. Film casting basically is first dissolving the polymer pellets that's usually in like in the granules form, let's form in a solvent, and you're creating a solution of the polymer like that, and then use a mandrel basically, and then do a deep molding. So you cast, like you put this through the solution, and the polymer could be coated on the surface of this mandrel. So when you pull this out from the solution, you will have some thickness of the solution coated on a mandrel, and then these would go through some heating ovens, and the solvent would be evaporated. In that case, a solid layer of the polymer would be formed on the outer surface of the mandrel, and a tube would form. And you do this in, in cycles. Each cycle would coat about 1/10 of tau inches of polymer on the surface. So if you go 10 cycle, you coat about 1 tau inch of or 0.001 inch of polymer on a mandrel. So each polymer has a different type of solvent that is compatible and is good for that polymer for casting. For example, PBAX usually uses M-cresol as a solvent to make a solution. This solvent is of course toxic, and it has a high boiling point. So there are some environmental concern about that one. And then you typically dissolve about 10 to 20% of PBAX in that solvent. And the very important thing here is controlling the viscosity, because the viscosity would determine how much thickness, how much coating you do on a mandrel. For polyimide is a different things. Polyimide, as you cast, a chemical reaction also takes place. So you have NBP with the polyamic acid as a precursor that make a solution. But when it goes to higher temperature, a chemical reaction would take place that we will explain in the next slide. And a polymer would form. In that process, actually water is released and it has to get out of the system. For PTFE, it's a very strong polymer. It's a very, very neutral polymer, and it doesn't dissolve in any solvent. So what they do is that they disperse the PDF in a aqueous dispersion is with water basically, and use a surfactant to disperse the PTFE particles. As you can see on the bottom left, PTFE particles are dispersed in the solution, and what you do is that when you do is the same mechanism of casting. So it goes through the solution, it will get coated on a mandrel, but the first thing that you do is that you remove water. So these particles now, they are close to each other and they get connected through van der Waals forces. Now you heat them more, and as you heat it more, a process is started that is called sintering. And a sintering is that you diffuse all these basically particles together to form a solid layer that is called sintering. Basically you are you're creating a very, very solid thickness on the surface. So as I mentioned, you do this in a layer by layer form, and each layer you do like 1/10. So the reason for that is that this would give you the controllability over the process. If you go too fast, there is a chance for solvent to get trapped. It doesn't evaporate, so you create a porous structure. And at the same time, if you go too fast, it would be difficult to control the thickness. So doing it gradual with increment of 1/10 of tau each time, it gives you a very good control on the process and also on the tolerances that you want to achieve. So we mentioned that a polymer is coated on mandrel on increment of 1/10 of tau, and as the solvent is evaporated. So I have provided a sketch of how like the wire or mandrel is coated. So first it goes through like a bath of the polymer. On the right side there is a polymer solution that go through that polymer solution. The polymer is coated on a mandrel, and then it goes vertically through some heaters, and then it goes, through different cycles. So each cycle would add, its thickness to the polymer, and eventually you get to like 1 tau or a 2 tau thickness that you want to achieve. So for polyimide specifically, as we explained before, it is we call it imidization process, and a chemical reaction would take place. We have different types of polyimide. For this one, for example, is a Captain one, and for a Captain, the structure is aromatic. So when it's formed, the water is released, and the water has to be separated from the. I mean, it has to be evaporated and get separated from the polymer. The popularity of the polyimide is that because it's a very, very strong polymer. Is after PEEK and PET is the polymer that is very strong. And because it has a very good strength or a high modulus, it can be actually produced in a very thin film. So with 1 tau of polyimide, you can get a very good strength that would be enough, to make your catheter potentially. One more important thing about polyimide is that it is a thermoset, so it will not melt or reflow for, if you want to do other processes on it. For PBACs, polyimide or other types of polymer, the viscosity and number of passes would determine the final wall thicknesses. And for TPU, we can go as low as 80A, and for PBACs, we can go as low as 45D in diameter, basically. the the time that we do film casting versus extrusion is that when we want to combine different polymers like PTFE that we cannot extrude. And we need PTFE as a liner because it has a very low friction factor, and it has to be used as an inner layer for guide wire to go in. And to combine it with the other layer, the film casting is a very, very good option because you can cast on PTFE. And we have explained this in our previous video that how this, multi-layer casting will be done, and we will also explain in the next slide that how this layer would be, get combined eventually. But with a PTFE as a liner, you can cast on it in a casting process and create a structure. And you have different, application. Like for example, you have, very soft material for neurovascular applications, catheter, or you can go to a little bit, harder material. And one very important thing about PTFE is that is neutral, and it would not basically get wet. So usually we measure a contact angle, like you put a drop of water and measure the angle that it makes with the surface, and it would show that how much contact angle or hydrophobic properties you have on PTFE. One other thing is with PTFE is that you can also measure it with the XPS technique. So for when you cast PTFE, after that you have to etch the PTFE. So you have to remove some of the fluorine group from the surface to be able to bond it to the other materials. And that's why you have to control the contact angle or wettability of PTFE. And we'll explain it in the next slide in more detail. The other important thing is that the mechanical properties of a film cast, how mechanical properties would be driven. by your process. If your process is good, that is, like you're using a very good mandrel, your wire is very smooth, there is no rough surfaces, and if you are evaporating all the solvent, there is no residual solvent trapped that could be, toxic or, create poor structure for you, and your film is solid, then your final properties, your final mechanical properties of your fin cast is only rely on your polymer, on your resin, and that's it. So if you are using the same resin as your competitor, then you should get the same mechanical properties. I've seen that some people, they claim that, oh, we got a fin cast that is twice or three times, stronger than other material, but that's basically is not true. Is that means that you have you improved your process, you reduce your defects now that your mechanical properties has increased, basically. So you reduce your defects that you have during your process, and now all these noise that are gone, your mechanical properties will be controlled by your resin. So as your molecular weight of your resin goes up or goes down, your mechanical properties would get impacted. And the resin, there would be very little control over the resin. Basically, whatever supplier would give you as a resin lot in that time would be what you have, and you have to see how much would be the lot to lot variation. When you remove all the other noises, then you can see that, okay, now this is the the effect of the resin, how much would be on your tensile, on your yield, on your elongation at break, or other properties. We have explained this before, but just as a reminder, PTFE has 4 fluorine group on the surface that make it very, very neutral and hydrophobic, and it would be very difficult to bond with the other material. So what you do is that you etch the surface, and with etching, basically you knock off 2 fluorine group from the surface. When you basically knock off these 2 fluorine groups, you can use a primer, basically, and the primer would replace the fluorine group with more functional group that is more it can react with other material more easily. So basically when you're doing that, is that you making the bond with outer jacket stronger. If you do not etch properly, the bond between the PTFE and outer jacket would be weak. Or if you don't use a primer, the etching effect could diminish over time, and you lose that etch properties for your polymer. In our previous post, we explained that why braiding using catheters. We explained that the braiding would improve significantly the torqueability and pushability of catheters. We have different types of braiding. It could be a coil, it could be a braiding, and in analytical polymers, we have capability to identify the polymers. We can analyze the catheter structure. For example, for this commercial catheter, you can see that the PTFE liner it doesn't have a good bonding, and it would come off easily. The total thickness of 7.5 tau, you would have 1.5 tau PTFE layer as a liner. And then you have the coil on top of that, and then you have a braiding, and then you have PBAC 74 as basically the jacket on the top. So PBAC 74 and the braid altogether is 5 tau. And you can see that, on distal versus proximal, you can have different configuration of like braid or braid and coil, because you need different configuration of torque for each side. Each polymer has a different application. Um, Polymers are different in chemical compositions, and because of that, the physical and mechanical properties are different. PTFE is very, very neutral. It's not bonding to other material, has a very low friction factor, and that's why it's used as a liner. PBAX is a copolymer, so you have nylon segments that would act as a hard segment, and a polyether segments that are very flexible and soft. As you increase this ratio, like if you increase the polyether, you can produce material with higher diameter, so it becomes softer and softer. For example, a PBAX 72 has 20% of polyether. If you go to a PBAX 35D, has 75% of polyether. So you can produce, but it's the same chemical structure, but you are changing the ratio between the two. PDMS silicon, they have these SiO bonds that is very, very flexible and is very soft. For polyurethane, it's the situation is different. First, I have to mention that picture in the center of the slide, that is a balloon, a PBAX balloon, and it shows that how the hard segments, they are dispersed within like an ocean of soft segments. So they are like segmented, hard, polyamide or nylon portions that are dispersed in polyethers. Back to polyurethane. Polyurethane is similar to PBAX, but you have a lot of options with TPU. With TPU, you can have different hard segment. You can have, polycarbonate-based polyurethane. You can have polyether-based polyurethane. You can have polysiloxane-based polyurethane. So, and you can, within that also, you can change the type of the hard segment. So you can go aromatic, for example. For this one, you have the aromatic rings in the structure. You can go aliphatic one. And within that, even that category, you can change the ratio of hard to soft segment. And basically you change the diameter of the polymer. So you can go softer, you can go harder, change the ratio between soft to hard segment. And you can generate a lot of different properties. For example, for like polycarbonate base or polysiloxane base polyurethane, they are more resistant to chemical environment. That's why they are more suitable for implant application. They are stronger. Polyether polycarbonate is more like flexible. It has a different properties when compared side by side. So because of those variability that you have and options that you have a lot of polyurethane in the market. And you have Ticoflex, you have Carbotane, you have Palatane, Ticotane, that the chemical composition are they are changing, and the diameter is changing, the aliphatic or aromatic also changing. So you have a lot of options compared to PBAX. So extrusion would come in play when you have a wall thickness of greater than 2 tau. Like below 2 tau is very difficult to control the extrusion process. So 2 tau and above is that when we start doing the extrusion. And extrusion basically the principal mechanism is that you melt the pellets and you form it into a continuous tube form. In extrusion, you can do also co-extrusion, different layers of polymers. You can do, like for example, HDP as an inner layer and a PBAX as an outer layer, but you need a polymer in between that would be like a grafted molecular material that will bond the two together. For extrusion, the very important factor is resin what MFI or intrinsic viscosity, that is both represent molecular weight, are using, the moisture and additive, if like a master batch or something, what kind of additive are added into the polymer, and the extrusion itself, that all the process parameters that is there, and what tube size, what dimension, what tolerance you are targeting, and then the inspection of that part when you produce it. How are you going to inspect for OD, for ID, wall thickness, tensile testing, for measuring the mechanical properties of the material to make sure that the material has the integrity and the strength that you need for your final product. After you produce the part, the very important thing is the aging effect, like how much time, temperature, moisture, and light would alter the final product. And basically, how do you evaluate your final product? What is the tube performance? Like when that part is shipped, what kind of dimension you have to, it has to be the deliverable from the tube, what dimension, the burst, the tensile, and the visual that you expect, basically. So this is kind of overview of the extrusion, and that will help how to validate the process. What when you do validation or DOE, how do you capture your factors that are determining the final properties.